Today we have George Lu from UT Austin talking about adaptive succinctness in computational secret sharing.
Yeah, I can start. Yeah, so yeah, hi everyone, I'm George, and I'll be talking about adaptivity and succinctness in computational secret sharing. So we can start with what exactly is secret sharing. This is a pretty, let's say, self-descriptive cryptographic primitive where a dealer has a secret in mind, and his goal is to split the secret into a bunch of shares with the property that given with a set of shares along with this like policy function with the property that if there's a subset of shares which satisfy this policy, these groups of users should be able to recover the message. But conversely, any subset of users which don't satisfy this access policy, they should learn nothing about this secret. So a natural question to ask, of course, is what policies can we secret share for? And the study of secret sharing really started with the works of Shamir and Blakely, which showed how to secret share for threshold policies. Now, of course, we know how to do something much more general, and turns out we can share for a much more general class of policies than just threshold. For example, in the work of Demal in the 90s, he showed how to share for monotone span programs, which captures a class of monotone Boolean formulas. However, both of these constructions, both sort of are both settings of information-theoretic secret sharing, where the security is information-theoretic. And like much else in crypto, if you're willing to assume computational assumptions and computational bounds on the adversary, we can actually support much broader classes of policies. So the go-to example of this might be the secret sharing for monotone circuits of Yao and Vinod and friends. And in addition, or the secret sharing of monotone MP from Komorgatsky and friends. So in this talk, I'm going to go over two results. So the first is we can using the very, I guess, hopefully simple tool of one-way functions, we can turn any computational secret sharing scheme from statically secure to adaptive. And in the second part of the talk, we'll use some heavier cryptographic tools of indistinguishability obfuscation, as well as one-way functions to construct a computational secret sharing scheme that's succinct. And yes, these are two joint works from Crypto and Asia Crypt with Brent and Shafiq, respectively. So let's jump right into the first construction, which is going to be adaptively secure computational secret sharing for any policy class. So when discussing the security of a computational secret sharing scheme, the security is usually defined in some game-based definition. And this usual notion is a security game, where an adversary picks some subset of users to corrupt. And now when the secret sharer shares a secret, the adversary gets to see that subset of shares. And the adversary and then has to guess a bit or a message that the adversary has shared, that the dealer has shared. Now, we can also define a stronger and maybe more natural notion of adaptive security for secret sharing, where instead of committing to this set of corrupted users up front, the adversary can look at a single share and then use information perhaps related to this share to decide on its future corruptions. And once again, the adversary can corrupt any subset of users that doesn't explicitly satisfy the access policy before guessing a message. So why do we care about adaptive security? Well, for one, it should be pretty easy to see that this adaptive notion of security does imply the static notion. And since it's a stronger definition, why not if we can prove it? And in addition, for applications where you use secret sharing down the line, this could also imply adaptive security for a set of primitives. In addition, even as a standalone primitive, I would argue that standalone definition, this is maybe a more natural definition, where we, instead of thinking of an adversary as maybe a fixed set of users that's really out to get you, maybe it's maybe these users are being hacked or being bribed, and the person who really wants to discover your secret can make decisions on the fly to corrupt individual shares. So in our first work, what we achieve is that we show for any given a statically secure secret sharing scheme for any policy class P, we can transform this into an adaptively secure one for the same policy class using one-way functions. And so this only incurs a polynomial security loss and blows up the share size quadratically. So as a high-level blueprint of how we're going to do this transformation, starting with our statically secure secret sharing scheme, we're going to use this along with symmetric key encryption to achieve a very mild form of adaptivity, which we're going to call semi-adaptively secure secret sharing. And then it turns out that this will be both pretty easy to build, but this limited amount of adaptivity will be useful in allowing us to get to the full notion of adaptive security for secret sharing.
So what should I think of for the static scheme? And like, is there a concrete example I can think about for the static scheme?
So you can think of these most computational secret sharing schemes, like you can think of Yao's scheme. We only know it's statically secure in general.
Why is Yao not adaptively?
Because if you want to adaptively corrupt a set on Yao, your reduction essentially has to do a adaptive selective opening style attack or selective opening style reduction. So we do know some limited results. Daniel had some works on if the depth of these monotone circuits is logarithmic, they are adaptively secure. In addition, right, if you're willing to take a sub-exponential loss in security, you can just guess the corruption set through complexity leveraging, and that does give you adaptive security. But in general, we don't expect something like Yao to be adaptively secure.
Is this also related to adaptive gambling or adaptive gambling? I mean, Yao is related to gambling.
Yeah, so I mean, Yao's secret sharing is kind of like just Yao's garbling, except you only have the one wires instead of having 0 wires, you just have nothing. The arguments for showing the adaptivity of the limited set of adaptivity for Yao's secret sharing are very similar to Yao garbling. I would say in general, we don't know any the techniques in general, other techniques for adaptive garbling, we generally don't know apply to secret sharing. And this is mainly because in the garbling setting, you usually have either a 0 or a 1, right? And then this helps you do some form of equivocation, and it doesn't seem clear that setting can translate to secret sharing. Make sense? Or okay, yeah. So yeah, to maybe discuss our results a little more formally, let's just look at the syntax of a secret sharing scheme. So the secret sharing scheme, we're going to consider two algorithms. There's going to be a share algorithm, which takes in the security parameter, the access policy, as well as the message, and decomposes this into a set of shares, and then a reconstruction algorithm, which takes in some subset of these shares and tries to reconstruct the message. And here we'll also have the addition of a public share, which is always present. If you're thinking in some specific example like Yao, the public share is just all these encryptions of the wire values. And then here M will be the number of users. So let's talk about what I mean by semi-adaptive security from 2 slides ago. If you recall the static security game, what it kind of looks like is that the adversary commits to all their inputs up front. The policy, a set of messages, as well as a set of corrupt users. And then the challenger has to return all of them before the adversary has to guess which message the challenger has encoded. Now, in contrast, in the adaptive game...
What is that again?
Oh, so PS is the public share. So yeah, you should think of it as maybe in Yao as the ciphertexts of the wire labels. It's not in something like, I guess, yeah. So in something like Tremere secret sharing, right, there really is no public share, but this is I guess this is maybe a slightly more general definition where you can have this, but if you want to think about without loss of generality, you can always push the public share by repeating it in all the user shares. Right. So in the adaptive security game, the adversary starts by committing most of these same inputs, including the policy as well as a set of messages, and simply receives a public share. And then in the second phase, they're allowed to corrupt these user shares one at a time before guessing a bit B. Now in the middle, for our notion of semi-adaptive security, instead, the adversary starts by just committing to the number of users and then getting the same share corruption phase that they do in the adaptive game. But importantly, they only get to do this before actually seeing the public share of the scheme and guessing a bit B. Yes?
So if a scheme doesn't have a public share, then semi-adaptive and adaptive are the same thing?
If a scheme doesn't have a public share, then yes. But I guess, so first of all, I guess maybe you're getting a little ahead of me. So first of all, if you look at the semi-adaptive definition, it maybe doesn't quite make sense with the syntax of secret sharing you've given so far, right? In particular, how do I generate these user shares without knowing the policy and the message? And so we're actually going, just for the purpose of our semi-adaptive definition, we're going to consider like a slightly more structured syntax of secret sharing, where our share algorithm is decomposed into a share key and a share message, where the share key only needs to take in the number of users and generates the shares, and the share message, of course, generates a public share. Now, this is useful for two reasons for us. One is, of course, it makes our definition of semi-adaptive actually type check and make sense. And another thing I want to point out, that which will be useful to transform this into an adaptive scheme, is that we can actually run share message on multiple different messages and encode multiple messages under the same set of user shares. And so maybe one way to think about this is some version of secret sharing that's a little bit more like an encryption scheme. Okay, so how do we get from static to semi-adaptive? It's actually quite simple. Given that we're using symmetric key encryption, all we do is that when we share a key, we just share a fresh symmetric key encryption key. And when we want to share a message, we simply publish the entire statically secure secret sharing scheme as a public share, where each of the user shares is encrypted under their respective symmetric key. So why is this semi? Okay. So yeah, the shares of the semi-adaptive scheme are just symmetric key encryption keys, and the message share is going to be the entire statically secure scheme, both the public share and the user shares of the static scheme, except each of the user shares are going to be encrypted under their respective symmetric key. Right, so this is just encapsulating the static scheme in a layer of like symmetric encryption.
So for the ciphertexting the public share?
Yes. So whenever you get the public share, you get all of these ciphertexts. Okay. So why is this semi-adaptively secure? Well, the important thing to note here is that in the semi-adaptive security game, because the adversary only gets to see the public share after they're finished with corrupting user shares, the challenger can incrementally replace using symmetric key encryption, replace any share that the adversary didn't corrupt with a share of 0. And now, once the challenger is finished erasing these corruption queries from the view of the adversary, it can directly rely on static security to argue that the message is computationally hidden. So that's the static to semi-adaptive transformation. And now, how do we use this limited amount of adaptivity to go all the way to the notion of adaptive security for secret sharing? So we can imagine we have our semi-adaptive scheme. Let's say a user has their share, and we want to encode the message in the share. Now, the main limitation of semi-adaptivity is you only get adaptivity until you see the public share, right? And so the idea here is we're actually, rather than directly giving this user their share of the semi-adaptive scheme, we're going to encode it in another layer of secret sharing. And now the user won't receive, instead of receiving their share in the clear, they'll receive an encoding of their share, which they'll only be able to access given the ability to reconstruct this second scheme. And it turns out doing this once won't be enough. So we'll actually have to do this up to n times, where n is the number of users in the scheme. And finally, what the user's share looks like is going to be a set of public shares encoding their respective user shares in all but one of these schemes, in addition to a single user share in the clear. So sort of zooming out to an example 5 user scheme, what does everything look like? There's going to be essentially 6 instantiations of the underlying semi-adaptive scheme. Each user is going to have their level 5 scheme shares in the clear and use them, and these are going to be used to encode their level 4 shares, and then level 3 shares, and level 2, and level 1, and level 0, and so on, where each user's individual share, of course, is this entire vector, and the public share is simply the share encoding the message. Now, as a sanity check, why is this even correct, right? Well, we can see that if we have a subset of users that comes together and is authorized to satisfy the policy, then because their level 5 shares are in the clear, they can use it to decode their level 4 shares, and then use them so on to decode their level 3, level 2, level 1, and so on, and then finally recover the message. Now, for the other part, why is this adaptively secure? So if we think about what the adaptive security game looks like when instantiated with this transform scheme, when the adversary corrupts a user, they receive this vector of shares. And the key observation is that on the very last corruption query the adversary makes, regardless of to what particular user it is, this public information, when the adversary receives this public information, they'll receive no more user shares, almost by definition, because this is the last corruption query the adversary makes. And therefore, our challenger can rely on the semi-adaptive security to erase this user share. And it turns out this observation is true for every share in this last row of the secret sharing scheme. But once this is all erased, the next observation is that if we zoom in and just consider the level 0 through 4 secret sharing schemes, this has effectively turned the second to last corruption query to the last corruption query. And now we can once again rely on semi-adaptive security to say that to erase the share information in the second to last scheme. If you kind of repeat this logic, what you end up with is that the reduction only has to give out this degrading like staircase of shares. And what's important here is that the level 0 shares, which are the only shares which actually encode the message, the reduction never has to give out. And as such, you can directly use the semi-adaptive and in fact static security of the level 0 secret sharing scheme to erase the message. So this concludes the first part. I guess, is there any questions or?
I did not fully understand the last page.
Okay.
So why can't you just change every shares in the box to be 0?
Why can't you change all of the boxes?
Yeah.
Well, so the security property you have of the underlying scheme is like semi-adaptive security, right?
Yeah.
So the observation is that you can change it to 0 if I sort of know that I won't be giving out any more user shares of that scheme in the following scheme. So in particular, right, you could ask, why can't I change this to 0? Well, that's because when I'm at the second to last corruption query, I don't know what other shares I might have to give out on that scheme. And so it's not semi-adaptively secured. Yeah.
I don't think I understand like when exactly these different shares are given out. Like when in the protocol does the adversary get each level?
So each user share of the adaptive scheme is going to be this like row. And so when the adversary makes a corruption query, what they see is like a single share maybe out in the clear, and then a bunch of what look like encryptions of shares, if that makes sense, and there's going to be like around n of them.
So the adversary gets the whole vector at once.
Yes, when they make a corruption query, they get like a row of this.
So how does the dealer know when to give out zero versus real?
Because the argument here is only dependent on the order that these shares are given out, right? So if you make the first corruption query, I know that it's the first corruption query because I am the dealer. It doesn't matter which particular user this corruption query is on. Yeah.
So every corruption query I give out, like, what? How do I know it's the last one?
So we kind of just trivially bound it by saying if the secret sharing is on end users, then they can make, the adversary of course can make up to
Sure.
n corruption queries. If you have some better bound based off what your policy is, you can use less layers, I guess. Good with everyone?
Yeah,
All
I think I understand.
Okay. And okay, so the second part of this talk will be on getting.
If the final work there's no work on adaptive security. How does it compare with previous?
So there's nothing. So I think the best thing we knew before was either you can complexity leverage and you incur sub-exponential loss, or I think effectively there's some like more clever ways to complexity leverage. If you sort of constrain the structure of your circuit a little bit. Like I think the go-to example is this where I think, in fact, maybe the only example that I'm aware of is this work from like Daniel and one of his students where you can complexity leverage and your loss is based either on the like minimum of the depth or the height of your circuit rather than just like the entire size of your circuit. But in general, we didn't know anything generic, and in particular, even for this other work of like secret sharing for monotone NP, nothing. There was no like. So the previous scheme, I think, maybe it depends on how I guess how sub-exponentially secure you believe your underlying primitives are, right? If you only believe in polynomial security, then really there was no, I guess, analog in the previous settings. If you yeah. So it's like if you wanted to do so the size of this grows like, as I said, like like you have like an n squared size blow up. If you're in sub-exponential security, if you believe in like 2 to the root n security, then it's probably roughly equivalent. If it's higher, if it's lower, it'll be different. Yes. Yeah.
Is adaptive security equivalent to non-adaptive static security in the information theoretic regime?
So it's not so it's not equivalent, but it is the case that these examples of like Shamir and like monotone spam stuff for monotone spam program, those are all essentially like perfectly secure or like statistically secure on like all subsets, and in that case that is stronger than adaptive security. But you could come up with like contrived schemes where you satisfy this like static security game but not the adaptive security game.
Even information theoretically.
Yeah, so I can give you an easy example. So if you think about Shamir secret sharing on like T users, this of course is perfectly secure, right? But I can imagine Shamir secret sharing a message and then sharing the same message additively on like a random subset of like say T-2 of the users. And then on each share, I'm also going to tell you what this T-2 size subset is. So this is statistically secure because if the adversary guesses like less than T users, right, they're unlikely to hit this T-2 subset. But if you're able to adaptively corrupt, right, you look at one user's share, it tells you what this hidden subset is, and then you can corrupt that subset and recover the message. Though to my knowledge, nothing information theoretically and non-contrived is not adaptively secure. Right. Everyone? Okay, cool. So for the second part of this talk, I'll be discussing succinct computational secret sharing for monotone Boolean circuits. So succinctness is a very natural property that people wanting cryptography take any host of cryptographic primitives. Some people have probably asked, like, how succinct can we make it be, including the big one of snarks. And yeah, this is by no means a comprehensive list if I've missed your favorite succinct primitive. So in the context of computational secret sharing for monotone Boolean circuits, what do we know? And by monotone here, I mean that the circuit has no NOT gates. So we have the original works of Yao and Renaud, where there's essentially no succinctness, and the share size is proportional to the circuit size. And for a long time, we really didn't know anything much better. Fairly recently, in 2023, though, there was a work of Applebaum et al., which showed that you can compress the secret sharing scheme to where the share size is independent of the fan-in of the gate. So you can have very large fan-in and fan-out gates, and you can essentially do that part for free. But maybe what's the best you might hope for is something that might be independent or logarithmically dependent on the size of the circuit in general. And so in our result, we show using polynomially secure IO and one-way functions, we can build a statically secure computational secret sharing scheme for monotone Boolean circuits. And we use the same syntax as our prior result, and where the public size here grows only linearly with the number of users plus some poly factors in the security parameter, and the user's share size is exactly security parameter. So as the theorem statement kind of alluded to, we are using obfuscation. So let's look at what a natural way to build secret sharing from obfuscation might look like. A set of user shares are just going to be random strings, and the public share is actually going to consist of an obfuscated program, which hard codes the set of shares, the policy, as well as what the user shares should be. Now, if you're given a subset of shares, what the natural thing to do is this program is going to take in the subset of shares, check that it's in fact equal to the set of the real secret shares that it's hard coded inside it, and then use that, evaluate the circuit on that subset of shares, and if the circuit does indeed verify, it's going to dump out the message. So this is essentially how they build secret sharing for monotone MP from the work of Kumargatsky et al. But our goal is to make the secret sharing succinct, right? So the only big thing was the circuit policy, and maybe a natural first attempt is let's, instead of giving out the circuit policy, let's have this program just have a hash of the circuit policy. Since at reconstruction time, the users know the policy circuit, we can have them feed it into this obfuscated program as well, and use that to, and now the program can simply compare this hash and see that this is hopefully equal to the hash that it has hard coded, and then do the same computation. And now the natural question here is, well, if we just do this, is this succinct? And so the answer there actually, yes.
Don't you need to also hash the shares themselves inside the program?
The shares themselves don't grow with the length of the, right? We're trying to make this program short with respect to the size of the policy description.
Oh, okay.
Right. So yeah.
So you need to be
No, so our thing is not independent of the input size, and I think that is an open question, I think, in getting something that, so yeah, if you remember from the previous slide, our public share size grows exactly n, where n is the number of users, plus some poly factors, but the thing we're trying to minimize is this dependence on the policy, the description of the policy.
But in the previous scheme you described, each of one person's share had size n, right? So if your program public share has n shares, isn't that n squared?
Wait, so first, I guess, this is a different construction. Like are you talking about the adaptive construction? So okay, so this is a different construction. We're only going to show static security for this one. if you're thinking about sort of the composition of the two, yes, that like you can, like, given this and the prior result, you can have like a n cube size adaptively secure secret sharing scheme. But in both cases, right, like the dependence on the number of users is not tied to the dependence on the size of the circuit, right? Like the size of the circuit is lower bounded by the number of users, but you can imagine there could be very large circuit policy classes, which could be like n to the 5th or n to the 10th. So where was I? Yeah, so if it's succinct, and of course the answer there actually depends on what kind of obfuscation you have. So if you're in this happy dreamland and you had ideal obfuscation for Turing machines, then what I described on the last slide would very directly give you succinct computational secret sharing. Unfortunately, to my knowledge, we don't have this, and we are in this very sad world where all we have is I/O for circuits.
Unbounded input length and you can do it computational.
Yes, I will mention that in a couple transitions. And so fortunately, this idea of sort of getting more expressive like models of computation from I/O for circuits has been considered before. So namely in our work, we kind of take some of these techniques from I/O for Turing machines of bounded length inputs, and along with some additional observations of our own, and show that it is sufficient for succinct computational secret sharing. Yes, there was this prior work also for I/O for Turing machines of unbounded length input if you have propositional proofs of equivalence. And actually a concurrent work of ours from Vishek, Zhang, Daria, and Omer sort of also recovered this result of succinct computational secret sharing viewed through this lens of propositional proofs.
So can they then resolve the dependence on the input?
No, I think their scheme is asymptotically the same as ours. Yeah. Any questions?
Wait, what if they use my paper? Can they get rid of?
So I guess I don't want to say anything like I'm not too sure, I think is the answer. Their paper is not public, so I only know what I secondhand like have been told from Surya, but there are some like it does seem like you need this like input length to sort of embed the adversary's like challenge input somewhere. And it seems hard to embed this actually in the user shares. So like the only way we know how to do this is kind of doing it in the public share. I think this is kind of, yeah, this seems kind of independent of, I think the way Sari described it is the size of your propositional proof actually does need to grow with this number of users. So even in that setting, it seems unclear if we can do better than a user length dependence. So let's go over like a high level view of how I/O for Turing machines actually, you get I/O for Turing machines from I/O for circuits. And the basic idea is, well, we have this input tape for the Turing machine. And what our circuit is going to, we'll have an obfuscated circuit, which is in charge of two tasks. The first is it's going to act as a step circuit and compute a single step of this Turing machine. And in addition, it's going to assign this state to sort of certify the authenticity of this computation. Now, this circuit can be small, and it can just compute these Turing machines, these steps of the Turing machine. And of course, once you finish, it can compute an output state, and that'll be the output of the Turing machine. And of course, for this to be secure, these intermediate states should be somehow encrypted. So our first observation is that for this setting of computational secret sharing, we don't really need to obfuscate the description, anything about this description of the circuit. And in fact, maybe an easier way to think about it is that the circuit, rather than being treated as an input to this Turing machine, is something more akin to the topology of this Turing machine, where we have these input wires and circuit wires, and we sort of hard code sort of the wire relations as sort of the path that this Turing machine takes. So this leads to a pretty simple and natural construction of the succinct computations of computational secret sharing, where you have signatures essentially directly on the wire values, and what your Turing machine does, or sorry, and what your obfuscated circuit does, is it takes in as input, it checks these signatures, and if the signatures sort of satisfy the gate relation that it was given, it's going to sign the output. It's going to sign the output wire. Conversely, if you're not given a signature, this program should not, of course, sign the output wire. Now you can sort of move along, signing wires as you go, and if you're able to produce a signature on the output wire, this Turing machine should then just dump out the message. So now the question, of course, is this seems like a coherent construction. Is this succinct computational secret sharing? And now, and of course, if we had an ideal obfuscation of a circuit, it should be pretty easy to see that what I just described should be a computational secret sharing scheme. But unfortunately, we still only have I/O for circuits. And the main complication here is how are we going to argue security? Now, to talk about this, I'm going to have to introduce some I/O-friendly primitives for this purpose. And the main actor of this part will be I/O for circuits, where, of course, the main restriction of I/O versus ideal obfuscation is that you can only argue computational equivalence, computational indistinguishability when these circuits are exactly functionally equivalent. And thus, for these other tools, we're going to have to also look at I/O-friendly analogs, where instead of properties like unforgeability or collision resistance, traditional notions like unforgeability and collision resistance, we have to have some statistical guarantees on these primitives as well. So for signatures, we'll be using puncturable signatures, where in addition to the normal signing and verification algorithms of the signature, we'll also have punctured versions of signing and verification, with the guarantee that with using the punctured verification key, there is statistically no signature that verifies on the punctured message. And given the punctured signing key, the verification key and the punctured verification key are computationally indistinguishable. And finally, for this notion of hashing, we're going to be using the traditional notion of somewhere statistically binding hashing, which is a hash function, a compressing hash function, with the additional property that you can sample the hash key with respect to some hidden index, where the output of the hash now statistically determines the value of the block of that index. So, given these tools, let's try and look at what a natural way to prove I/O security would look like. So remember, the goal of the adversary is eventually to guess this message hidden in the obfuscated program. So the obvious goal should be, in our security proof, we should remove this message from our obfuscated program. And if you remember from the security of our underlying signature scheme and our construction, the only time that the adversary outputs this program is when it verifies a signature on the output wire. And so an actual intermediate goal right before that should be, we should be able to puncture the verification key on the output wire. So let's look at what a step of that proof might look like. On the input wires, we can simply not give them out. And so this allows us to puncture the signing and verification key. Now, if we want to move along and argue that the I/O program shouldn't be able to output an intermediate wire, we can do it in this following way. We can statistically bind to the hash of the output, the hash of the policy on that wire. And this sort of commits this program to saying, okay, the fifth wire is definitely an AND of X2 and W of this fourth and second wire. And then, because we know that this second wire doesn't exist, we can argue that our program, in fact, will never output a signature on the fifth wire. This in turn means that we can puncture this ability from our signing key, which lets us also puncture it from the verification key. And now we can kind of say, okay, well, our program is never going to verify on the fifth wire, and we can kind of move on and continue this argument. So if we kind of go along, we do end up able to prove security, but the issue is that if you look at what the verification key looks like at the end, we actually have to hard code a bunch of puncture points in our verification key. And it turns out this is too big. this is proportional to the size of the circuit itself. And of course, you shouldn't be hoped to be able to obfuscate a large program to look like a small program. So how are we going to fix this and sort of stop our IO program from needing to remember too much information? We're going to give it some additional external inputs. So just imagine for a moment we have like this long external string that our obfuscated program is only going to take a hash of. And what this string is actually going to look like is it's going to be a bunch of encryptions of wire values. In the real scheme, these are all going to be encryptions of 0. But in our proof, the first thing we're going to do is going to be to switch them to encryptions of the wire values on the circuit evaluation of the adversary's challenge input. And so, yeah. And then we're going to introduce the decryption key of these ciphertexts to the obfuscated program. So how does this help us reduce the size of the obfuscated program? Well, for one, we're going to change the program in 2 ways. One, it's going to take in these additional ciphertexts corresponding to the appropriate wire values. And it's going to have an additional check inside the program, where if the decryption of the ciphertext is 0, the program will never sign. Now, in a pretty similar way to the previous slide's argument, we can puncture these signing and verification keys. But the main difference is once we finish are making this argument and puncturing the verification key, we're going to just increment this counter. And we're able to do this, right, because that particular ciphertext is in fact an encryption of 0. And since it's statistically binding there, this is a functionally equivalent program. But what's important here is that once we've done this, we can actually erase all these punctured points on the signing and verification key and just rely on this external program to remember this, or sorry, this counter check to verify this. And we can sort of repeat the argument all the way down. And of course, once we're able to reach the output wire, we can say that the message is hidden and we can erase it from the IO program. Now, this seems like a bit of cheating, right? Because we also have this long external string, and this in fact is as long as a wire. But since it's external to the program, it's actually it's much easier to compress. And maybe the simplest way to do this is that we can just use FHE. And so in the real scheme and in the security proof, the reduction only has to publish an encryption of the input, and the reconstructors can sort of deterministically expand this to this whole ciphertext of the circuit evaluation. So what does our final scheme look like here? The public share includes a ciphertext encryption of 0, which can be expanded, and as well as this obfuscated program, which hard codes the verification key and signing key of this underlying signature scheme, as well as a bunch of hashes in the message. It takes in the gate values and uses them to output a signature or the message on the final wire. And of course, the user shares are just going to be the signatures on the input wires. So this mostly gets our site.
So I guess, why do you need this, why is it easier to use this Turing machine with unbounded input? And you can just get it from Turing machine for bounded input, and it doesn't have any poly law.
Sorry, you can get.
Is that like if you have for unbounded, what will be? Let's say I had Turing machine for obviously unbounded.
If you had obfuscated Turing machines for unbounded input, then essentially your Turing machine, like you could do kind of what I described on maybe like the first slide, where the Turing machine actually takes in the circuit description and just hashes it down, right? And just checks that the hash is equal to the hard-coded short hash of the policy function.
Because you don't want the obfuscated program size to be.
Right, the obfuscated program shouldn't hard code in the circuit or anything, right? That is the main restriction here.
Wait, so why can't you do it and do that? approach if it's bounded?
Because it grows like in the bounded setting, right? The size of your obfuscated Turing machine grows with the input length bound on your Turing machine. It's to avoid the poly circuit blowup, right? I don't want to take my circuit as input into right. Right. So this gets okay. So this gets most of the way to maybe the theorem statement earlier in the slide, but I've lied to you a little bit. Where if you remember the theorem statement, I promised you both that the public share size would be exactly n plus poly factors, and that we only use IO plus one-way function. So we kind of, in our real scheme, we make a couple modifications to what I just described. The first is that instead of using FHE, we can just use some one-time pad encryption along with some similar IO for Turing machine tricks, where we publish this short string, which is just the one-time pad encryption of the challenge input X star, and then an obfuscated program that has this PRF key that enables you to expand it out in this way. And then the other is, rather than using SSP hashing, we can use this slightly weaker selective notion of positional accumulators, which takes advantage of the fact that when these hash keys are generated, we actually know what the input circuit and reference string it needs to be binding on is. So you can think of this as the analog of this is SSP hashing is collision resistance, and this is some kind of target collision resistance. And so, yeah, to summarize kind of both of our results, in the first half of this talk, we showed how to construct adaptively secure secret sharing from statically secure. Applying this to the works of Yao, Vinod et al. And Komogotsky, we get the first adaptively secure secret sharing scheme for monotone circuits and monotone NP. In our second result, we show statically secure secret sharing with size dependent only on the number of users and independent of the policy size. And this does sort of compose with our previous result, give an adaptively secure secret sharing scheme with a cubic size, but still independent of the circuit otherwise. So there's some natural open questions in this area. So in the setting of succinct secret sharing, we could ask, can we do this from something weaker than IO? Can we do this for like more broader classes beyond like monotone Boolean circuits? And can we get, as maybe some of you have asked, like, can we get rid of this dependence on the user size? In the setting of adaptive security, I think it'd also be interesting if there's a reason for this quadratic blow up, or if we can do better with maybe even stronger crypto than one-way functions. Yeah, thank you. That's
Usually that one.
So I don't know if this is the actual motivation for why we looked at this problem was we were using it for some like multi-authority ABE, and we were like, so I don't know if you're too like, we had some paper on like multi-authority registered ABE. At the very end, we were like, yes, we should write we can do something from pairings, but we should add like a feasibility result at the end for using like IO and whatever you want to throw at it. And it turns out like maybe the functionality you get out of what you can get out of multi-authority ABE sort of corresponds to secret sharing. So you like obfuscate a secret sharing scheme, and then you do some like IO tricks to make it collision resistant and reusable so that it sort of forms the shape of a multi-authority ABE scheme. And of course, in that setting, right, if you want the scheme to be small or adaptively secure, the ABE scheme to be small or adaptively secure, that sort of corresponds to the adaptive or size of the underlying secret sharing scheme.